Hello, calculus fans. All right, we've got another integral where we're going to need to complete the square. So we're integrating 1 over 2x squared minus 12x plus 25. So let's go ahead and do that now. Let's complete the square in the denominator. That way, maybe we can see what to do from there. We might be able to do an inverse trig substitution or something else. I don't know yet. But we definitely want to complete the square. All right, so the first thing to do is just a little cleanup. We can't complete the square when there's a coefficient on the x squared term, so we're going to factor that out. And now we got to put something here. Now we've talked about how to do that. We have to take the coefficient on the x term, divide by 2, and square it. So we take the negative 6x, divide by 2 to get negative 3, and then square that to get 9. And that's the thing that we're going to put in. All right, now we can't just go around adding 9 any place we feel like it, so we have to compensate for that. We have to put something out here. Now at first glance you say, okay, well I added 9, so now I need to subtract 9. But we have to be careful. We did not really add 9. Look at what we added. If you were to distribute this 2, then the new thing that you really put in there was 18. So that's what we're going to compensate with. So now you should really be thinking about what happens if I were to multiply all of this out. Would I really get the same thing that I started with? I believe the answer is yes, because that minus 18 will cancel out with the 2 times 9 that you get when you distribute that. So it really is the same thing that we started with. Don't write equal unless the two things that you're working with are the same. They just look different, but they are mathematically the same. Should really point out that the equal sign is a special symbol in mathematics. It means something, and so you don't want to be too willy-nilly about how you use the equal sign. Okay, so we've completed the square. That x squared minus 6x plus 9 turns into x minus 3 quantity squared, and then the 25 minus 18 just turns into 7. Okay, so let's rewrite our integral. So we've completed the square in the denominator. And now I'm going to rewrite it in a slightly different way. I want to see the things that are being squared. So the 2 times x minus 3 squared can be rewritten as root 2 times x minus 3 squared. You should see what happens when you square each piece. And then the square root of 7 squared, of course, that turns into 7. Well, believe it or not, we can just write down our final answer now. Okay, now we're going to make a substitution. We're actually going to substitute for this piece in here. So we'll let u equal root 2 times x minus 3. That means du is root 2 dx. And we can clear that root 2 by just dividing by that thing. It's just a number, so we don't really need it. Okay, so now we can actually evaluate this integral. So we replace the u's in there, and it looks like this. And, okay, so forget about this. This is just going to come along for the ride because it's a constant. But for the rest of it, this piece here, finding an antiderivative, is actually something that we should know because we have a formula for that. So we're actually going to get this. So we have 1 over root 7 times 1 over root 2. Okay, now keep in mind that the 1 over root 2 just came along for the ride. That was from here. The rest of it, we'll see in a moment which formula we're using. So we're really getting 1 over root 7 arctangent of u over root 7 plus c. And then we can put the u back in. I've also taken the liberty of recombining these. And then this is actually going to be our final answer. And then, so the question that could come up is, well, how did we go from here to here? We're using this formula. The formula that the integral of 1 over u squared plus a squared du is equal to 1 over a arctangent of u over a. That's how we can go directly from here to here. That's actually worth knowing about. Okay, that's all for now.